we append them, so each iteration of the while loop takes constant time. In each iteration, we add some element to the output that will never be seen again. Sesim kapalı mı?
Hayır hocam, duyuyoruz.
Okey, tamam. Ses kapalı gibi bir şey gördüm de, tamam. That will never be seen again. Ha, o öteki bilgisayarın sesi, pardon. Şu projektörde öteki bilgisayar paylaşıldığı için. Bir yandan projektörden takip ediyorum da nasıl göründüğünü. So thus, the number of iterations can be at most the sum of the initial lengths of the two lists, which is linear. Okay? So the total running time is linear, ON, okay? So we're counting the number of inversions and we're doing the sorting part at the same time, simultaneously, okay? So we're using divide and conquer method, so we don't count each inversion one by one, but we have some observations and we have the possibility of counting multiple one of them at a single time, okay? That's why it's better than the n square exhaustive search algorithm, okay? So the total running time, so let's write the pseudocode for sort and count now. We sort and count the list, okay? If the list has one element, then there are no inversions. So the count is 0 then, okay? Else, we divide the list into two halves, okay? A contains the first dealing of n over 2 elements. B contains the remaining floor of n over 2 elements. So RA A is equal to sort and count A, and RB B is equal to sort and count B. Okay, so we sort and count the two halves simultaneously. Okay, recursively, let's say, not simultaneously, recursively. So and then we merge and count them. Okay, RL, we merge and count, and we already know how to do merge and count from the previous lesson. Okay, merge and count. A, B, and if. So then we return. There are three types of inversions, right? We have two lists, A and B. There are these inversions that are within A and inversions within B, and we calculate them recursively. And then there are another type of inversions which are between these two lists, and we talked about how to do it in the previous lesson last week. Okay, and then we sum up these three numbers to obtain the total number of inversions in the list. Okay, so return R, RA, RB, R, and the sorted list L. Okay, so that's how we do sort and count. For the complexity, we actually know that merge and count takes linear time, and we can apply the mechanisms of divide and conquer. So we can say that the two lists are of size n/2, 2 times Tn/2 plus linear time, which makes the total complexity n log n, as it is the usual case with divide and conquer algorithms. So since merge and count takes one time, the entire running time satisfies the recurrence Tn less than or equal to, let's say, because this is the upper bound, 2 Tn/2 plus Cn, where C is some constant. So we can say from our previous analysis, or Master's theorem also, immediately that Tn is n log n. Okay, so we can find the exact optimum solution in n log n time without having to resort to exhaustive search algorithms and without counting each and every inversion individually, by doing some a little bit more complicated operations with the divide and conquer method enables us to find the exact optimum solution in n log n time. Okay, the basic mechanisms of it we already focused on last week. This was the remaining part of the analysis. So this is the end of the part for finding the number of inversions. Now I will talk about another divide and conquer algorithm for another problem that we saw before, finding the closest pair of points. Okay, when I'm writing this, please try to remember the exhaustive search algorithm for finding the closest pair of points in a two-dimensional plane. Okay. And the complexity also. Finding the closest pair of points. So any one of you, please make us remember what the problem definition was, and another one of you, please tell us the exhaustive search algorithm. The closest pair of points. What was the problem? Exhaustive search. I think you were responsible for it for the midterm, if I'm not mistaken. But at any rate, we focused on it before. What's the closest pair of points problem? I will draw straws, bring them to the classroom next time, like in primary school, and pick any one of you. I don't know many of you, so I can actually look at the attendance sheet and ask one of you, but I don't want to do that. Okay. I know that it's tricky when you're a student in the class. You get too much stressed out that you will be picked that you don't even understand the question. So I don't want you to force them into it. But I think you remember the closest pair of points is problem. We also talked about, let me give you some clues, some many applications of this problem, like airplanes, possible crashes, finding the two airplanes that have the highest possibility of making a crash, or in image processing, clustering analysis, we said they were the applications. Okay, the airplanes, they are on three-dimensional, but think of them as two-dimensional. Which is the pair that has the highest possibility of crashing at any time? And you want to ensure a certain risk level, and you don't want any one of them to violate a certain distance requirement, a minimum distance requirement. Which pair has the highest possibility of crashing? The closest pair. So in the closest pair problem, what are we given? What is the input? Yes, in a two-dimensional plane, x and y coordinates of what? Of the airplanes in that example, but in general, the points. We are given a set of points with x and y coordinates because we are on the two-dimensional plane. And the question is to find what? The 2 points. The points, actually, the pair that has the minimum distance among all possible pairs, okay? That was the problem. So what was the exhaustive search, the brute force method of finding these? Let's say I have n pairs, n points, let's say. N points, not n pairs. How do I do them with exhaustive search, the one that has the minimum distance? We compute all pairs, yes. And to compute all pairs, I actually need to enumerate all possible pairs. How many possible pairs are there? N squared, but exactly how? Not plus 1. So y n minus 1 over 2. It corresponds to what? N choose 2. Okay, combination. Because I'm looking at two subsets of size 2, let's say. Okay. A set with n elements has n choose 2 subsets of size 2, right? So we look at all subsets of size 2. We are already given the distance between them. Actually, we are given the x and y coordinates, but we can compute the distance in constant time, given the x and y coordinates of both points. We enumerate all of them, which are like nn minus 1 over 2, and we pick the one that is minimum, so which makes it nn minus 1 over 2 n squared time, okay? So we don't want to use exhaustive search now. We want to use divide and conquer, okay? But let me write the problem again. The set of points P, P1, Pn, where Pi has coordinates x, I, y, I, okay? The distance between Pi and Pj is the Euclidean distance between 2 points. The goal is to find a pair of points PI, that minimizes dPi, Assume that no 2 points have the same x coordinate or y coordinate. Okay, how would you do divide and conquer now? In the exhaustive search method, we didn't use any geometric technique, right? I mean, we don't even need to draw it. We are given the pairs, we are given the x and y coordinates. We don't even have to visualize them. We can just calculate it by the distances, generate all of them, and find the pairs. Okay, we don't even need to draw it. It was immediate. But how would you apply divide and conquer now? In divide and conquer, we actually divide the input into 2 halves, right? And then do in one half recursively the other half, and somehow find the solution by merging or finding a relation between the 2 halves, etc. That depends on the problem. But how would you divide the input into 2 here? Into more or less similar sizes. And with size here actually corresponds to the number of points, right? Because my input is a set of points. So the size is the number of points in that set, the cardinality of that set. How would you divide it into 2? Think about it geometrically now. You are given many points, and you want to exhaustive search method was to calculate each and every possible pair, okay? But maybe I don't need to do that because actually, in order to avoid exhaustive search, I have to avoid doing that, okay? Maybe I need to find a mechanism to eliminate 2 very far points, okay? For instance, this one or this one. They are too far, and this too far, this needs to be quantified. So what does too far mean? We need a metric for that. And we need to eliminate calculating them because they are already cannot be the closest pair of points. Something like that, okay? But even before that, how would I divide the input into 2? What about the online class? Any guesses?
Maybe we can order the coordinates in an increasing manner, then we can calculate, divide it to a 2 problem.
To 2. So it's like, let's say this is the x coordinate, you mean, and this is the y coordinate. Ordering them is like, this is the minimum, the one with the minimum x coordinate, for example, this point, and the one is that point. You mean order them according to their x coordinate and take the first half, right? That's what you mean.
Yes.
Okay. Yeah, that's a very reasonable thing to do. And then we need to ordering them is like in this line, drawing a line in the middle, right? That's exactly corresponds to what you say. And the ones that are here on the left part of this line are one group. The ones on the right are another group, right? So we need to, if I know the minimum, okay, now as with our previous problem, I have 3 types of points. The points that are on the left region, both points are on the left region, okay? And both points are on the right region, and there are these points where one of them is on the left and the other one is on the right, right? There are three types of points now. And the ones on the left, let's say that I don't know how to do it yet, but I will find it recursively, okay? The pairs that has the minimum distance among all pairs that are in which all of them are on the left part, are on the left region, okay? Find the minimum one. On the right, find the minimum one. And what about the third one? Now we will find the minimum that one of them is here. Let's say the other one is on there. Among all these types of points, okay, find the minimum. The actual minimum, the minimum of the original, the entire problem is actually the minimum of these three, right? Minimum of these three minimums, right? We found the minimum here on the left region, the minimum among on the right, and the ones in the middle. So it's like, for instance, there are these first year students, second year students, and the one that has the highest possible grade. Oh, okay, not a good example. And there are these students who take both first year and second year classes, and all first year classes, second year. You take the one that has the highest grade in the first year, second year, and then among the ones that take both classes, and the highest one of them is the highest of these three. It's something like that, right? So, and we take the minimum among these type 3. So the first and the second, the ones that are both on the left and the ones that are both on the right, are done recursively somehow. I don't know how to do it, but recursively, I will continue dividing it into regions, something like that, okay? So the crucial point here is, as with the previous problems, what do I do with the points where one of them is on the left and the other one is on the right, okay? And for divide and conquer, I need to find a way of doing it in linear time, right? In order for the final complexity to be n log n, I need to find a way of doing it in linear time. But on the left, there are like linear number of points, n over 2, something like that, on the average, something like that. And on the right also, so I don't have a constant number of points. So I have many points actually. So do I need to check all such points? Just pick one point from the left, one on the right. If I check each one of them individually, these types of pairs, then this becomes something not different than exhaustive search, right? Because eventually, recursively, I will do the same thing, and it will not, because the operation there that I'm doing will not be linear time. So the problem here is, how do I do it in linear time? And we will see that for this, actually, we don't need to search the entire region. We're going to define and actually prove, not only define, a region that is like a boundary region. Okay, this is like the vulnerable region. If there are points that are the final minimum, it has to be in this region, and this way we will say that, okay, I automatically eliminate points that are like this, that are too far from each other. I will define a region in which there are not many points, and I will prove that if I search the points only in this region, that's enough and totally correct. That gives me the result. The others are unnecessary. Okay, I just need to focus on that region, and I will show how to do it in linear time, the entire thing, okay, in this region. Because it's linear time, and in recursive steps, eventually, I do this linear time operation, and the recursive steps take log n time, of course, and it will lead me up to n log n complexity, as it is usually the case with divide and conquer algorithms, okay? So that's the sort of like the headlines of what we will focus on this week. So assume that no 2 points have the same x coordinate or y coordinate. Divide the area into 2 halves Find the closest pair in the left half, find the closest pair in the right half, then use this information to get the overall solution. In linear time. Combining step. Combining step, it's actually the step that is executed in all of the recursive steps, okay? The combining step, the distances that have not been considered by either of the recursive calls are precisely these points, those points that occur between a point in the left half and the point in the right half. Okay? There are omega n square such distances, and we need to find the smallest one in ON time. Okay? So on a set, on a subset of points, let's say, begins with two lists. A list Px prime in which all points in pre-prime have been sorted by increasing x coordinates. Okay? Have been sorted by increasing y coordinates. Okay? So Q is defined as the set of points in the first dealing of n over 2 positions of the list Px. So this is like the left half. Okay. So it's like this region. I don't want to even go through. Okay. This region is called the Q region. And this region, we will call it the R region. Okay. Px, the left half, and R the right half. Okay. By a single pass, through each of Px and Py in On time, we can create the following four lists. Qx points in Q sorted by increasing x coordinate. Qy points in Q sorted by increasing y coordinate. Rx points in R sorted by increasing x coordinate, and Ry points in R sorted by increasing y coordinate. Okay. We are given the regions Q and R, and we can create 4 different lists. Qx is for the region in Q sorted by x coordinates, and then similarly for y coordinates, and for the region R also likewise. So for each entry, we record its position in both lists that it belongs to. Okay, one point is in either region R or region Q. Okay, if it's region R, we keep track of its position in both in Qx and Qy. If it's region R, then both in Rx and Ry. We keep track of it according to both of their x coordinates and y coordinates. For each entry, point, we record its position in both lists it belongs to. Okay, so combining the solutions, We will talk about it after the break. Okay? Because I need to, because I want to combine it with the lemma, the proof, and we will see it after the break, 10 minutes break. So combining the solutions, we will give the following definitions. Q0 star and Q1 star. Closest pair of points in Q, and R0 star and R1 star. Closest pair of points in R. Okay, so to explain it more visually, pardon. Neyse tamam. Okay. Yapacak bir şey yok. Biraz daha iyi ama az öncekiden galiba. So this is the line L. This is region Q and this is region R. Okay. Q0 star is this point. Closest pair of points in Q and R. Okay. These points are the closest points in region Q. Okay. And likewise, I have R0 star and R1 star in here. These points, these points, okay? And let delta is equal to minimum of the distances, minimum of the distance between Q0 star and Q1 star, and the distance between R0 star and R1 star, okay? Q0 star and Q1 star are already the minimums among in the region Q, and R is the minimums among in the region R. And I take the minimum of these two minimums, okay, and call it delta. And actually, the question here is, are there points that are so that one of them is on the left and the other is on the right, and the distances between them is less than delta, okay? For the points that are for which we already know for sure that the distance between them is at least delta, are of no interest to us because it's impossible for them to be the minimum of these three minimums, okay? If there are, for example, points like this, one of them is here and the other is here, and the distance among them is already greater than or equal to delta, then we are not interested in them. Because we know that there are already, because it's impossible for them to be the minimum of these three minimums. They are already greater than the others, the other two. So one of the other two candidates will be the kind of minimum. So we are interested actually in the points where the pair of points for which there is a possibility that the distance between them is less than delta, okay? So that's why we can actually bound our region here, because if the points like this, delta from here and delta from here, okay, the distance, because that is the region in which that's like the vulnerable region, in which there might be points so that the distance between them is less than delta. And so they can be the final solution. Arkadaşlar bilgisayarları açmıyorsunuz derste. Bunu dönemin başında söyledim size. Kapatın. Dinlemek istemiyorsanız gelmeyin. Yani burada projektörü boşuna yansıtmıyoruz değil mi? Bilgisayardan açıp dersi dinleyebiliyordunuz. Dolayısıyla şey yapacaksınız. So are the points. So are there points Q in Q and R in R for which distance between Q and R is less than delta. Okay? X star is the X coordinate of the rightmost point. In Q. Okay? So now I will write a lemma and then I will give its proof. Lemma is like if you have a big thing to prove, you divide it into certain parts, and lemma is some result, there's a statement, and there is its proof. You call it lemma rather than a proposition or theorem because it's a step. You will use the result that you proved there, you will use the result that you obtained to prove something else in the future. Okay, that's why it's called lemma. So if there exists Q in Q and R in R, for which dQr is less than delta, then each of of L. So what we will prove here is that if there are points like this is region Q and this is region R, for which the distance between them is less than delta, then each one of them is like in this region that I showed here, within data of this region. Okay, this is intuitive, but we need to prove it formally because one point might be here, okay, and another point here. So the boundary is that, okay, it's not there, but it's very, very close to the line, and it's very, very close to this left boundary, okay? And similarly for the other part, but we need to prove it formally, okay? So proof. Suppose that such Q and R exist. We write Q has some x and y coordinates, qx, qy, and R has some x and y coordinates, rx and ry. Okay? By definition of x star, we know that qx is less than or equal to x star, and that's less than or equal to rx. Okay? Because what did we say? X star, we defined it right before the lemma. I don't want to back it because it's too slow. You can look into your notes. X star is the X coordinate of the rightmost point in Q, okay? So if this is the region Q, X star, this is the point, and this is the X star, and it has a Y coordinate, okay? X coordinate of the rightmost point in Q, that's the X star. And because if such Q and R exist, then Qx is, because this is the rightmost point, suppose that such Q and R exists. So it means that the distance between Q and R is less than delta, and since the distance between them is less than delta, and Qx is less than or equal to X star, that is less than or equal to Rx, because, sorry, not I draw it at left, the rightmost point, the one that is the closest to the line, okay, in region Q. And because of the definition of X star, Qx is definitely less than or equal to X star, okay, because X star is the rightmost point in Q. And Qx is, of course, less than or equal to Rx, because Rx is in region R, okay? We are talking about 2 points. One of them is in Q and the other is in R. So obviously Qx is less than or equal to X star, and that's less than or equal to Rx. Does everybody agree? Are there any questions here? It's because of the definition of X star. Then we have now from here I write the following: X star minus Qx is less than or equal to Rx minus Qx. That is less than or equal to distance between Q and R, and that is less than delta. Here, because X star is less than or equal to Rx, I can immediately write this, right? Because X star is less than or equal to Rx, if I subtract Qx from both of them, then X star minus Qx is obviously less than or equal to Rx minus Qx. Does everybody agree? Does everybody agree? I assume yes. If you don't understand this, you won't understand the rest. So please ask if you don't agree. It just follows from here. Since X star is less than or equal to Rx, then if I subtract Qx from both of them, the same inequality will hold, okay? So Rx minus Qx is less than or equal to dqr, distance between Q and R, because dqr and dqr is less than delta, this is given, okay, because we said that suppose that such Q and R exist, and the statement of the lemma, please check into your notes, that if there exists Q in Q and R for which the distance between them is less than delta. So dqr is less than delta. Rx minus Qx is less than or equal to dqr because okay, this is Rx part and this is Qx, Rx minus Qx. Between them, it's the minimum of them. By definition of X star, Rx minus Qx is less than or equal to distance between Q and R. There exists such points, Q and R, and that is the following, okay? So, I continue writing down the inequalities. Because of that, Rx minus X star let me write, since Qx is in X star, Rx minus X star is less than or equal to Rx minus Qx, okay? Because Qx is in X star, I can write that Rx minus Qx is in element of X star. I can write that X star minus Qx, Rx minus X star is less than or equal to Rx minus Qx, and that is less than or equal to the same as before, distance between QR, and that is less than delta, okay? Since Qx is in X star. Okay, some manipulation, because Qx here we said that is less than or equal to X star, and that is less than or equal to Rx. So Rx minus X star is less than or equal to Rx minus Qx. It's like if X star, look at the relationship between X star and Qx. Qx is less than or equal to X star, right? Qx is less than or equal to X star means that minus X star is greater than or equal to minus Qx. So if I subtract X star from each of them, I can write that Rx minus X star is less than or equal to Rx minus Qx. So that is delta. So each of Q and R has an X coordinate. Within delta of X star and lies within distance delta of the line L. Okay, so that's the end of the proof. It formally proves that it's sufficient to focus on only on the regions that are delta distance from left and right of this line L. So the question here is, are there too many points in that region? I define the boundary of that region, the extent of that region, according to delta. And delta is defined as the minimum of the 2 points that are of the 2 recursive calls. Okay? We will show actually that there are not too many points in this delta region. And that's why I can do it in linear time. Because of the very definition of delta, I have restricted myself into a sufficiently big region, and in that region there are not many points. I can do it in linear time. By not many, I will quantify it in the proofs. Okay? So, any questions about this proof? It's a little bit of algebraic manipulation by using the definitions, okay? But intuitively what it says is that it's sufficient to focus on this region data, okay? Any questions? No? Okay. So, if we want to find a closed Q and R, we can restrict our search to the narrow band consisting only of points in P within delta of L, okay? Within this region L. So let S denote this set. Set of points in P within delta of L. Takıldı kaldı. Diğer Wi-Fi'nin de şifresi var dediler ama onun yeni gelen şeyler gelmiş de bu noktalara. Router'lar değil. Ne oldu şimdi? Ne oldu? Endnote'un mu sonuna geldik? Dondu kaldı. Hı. Sy is set of points in S sorted by increasing y coordinate. Okay. By increasing y coordinate, I have a list py. Okay, by a single pass of this list, I can find this. By a single pass through the list. Py, we can construct Sy in ON time. Okay, we can actually construct this because I have already maintained the list py, and Sy is the set point sorted according to their y coordinate. I am already maintaining this list from the beginning, so I can just by a single pass from this list, I can do this, okay? So every statement of the previous lemma is the following. There exists Q in Q and R in R, for which the distance between QR is less than delta, if and only if there exists S prime in S, for which D is S prime is less than delta. Okay. So that actually says that, okay, I have a line L and I have this region Q and region R. There exists points that the distance between which is less than delta, if and only if in S, and S is the set of points in the P within delta of this line L, for which the distance between them is less than delta, okay? According to these X coordinates. So there are such points, if there are such points that they are in this region, okay? So now I will write another lemma and we will prove it. S might be the whole set. S might in fact be the whole set. Let me also note this. S might in fact, it's possible, be the whole set E. Okay. So S is like, this part is S. Now I will write another lemma, which says that there are not many points in this region. Okay. And I will quantify what I mean by not many. So if SS prime is in S, it's in this region, have the property that the distance between them is less than delta, then S and S prime are within 15 positions of each other. In the sorted list SY. Each other in the sorted list. SY. Okay. So I have this sorted list SY sorted according to their Y coordinates, and if there are such points for which the distance is between two, and if let's say the list has 22 elements, I just made it up, and I need to check the first one and the 16th one, okay, in this list. It's not possible that there are points whose distances between is less than delta, so such that they are in places 1 and 17, 1 and 18, etc. Okay, it's always in this linear. There's like it's with at most 15 positions of each other. At most, it might even be less. So I will describe it and give the proof more geometrically. Okay. The proof is a little long, but I will start it in some point, and tomorrow we will finish it. Okay. But before coming to tomorrow's class, please review what we have done in this closest pair of points case. Okay. So because understanding this part of the proof, you need to really focus. Okay, there shouldn't be anything that is left not understood in the previous parts. So, sorry, I can still continue it. We have time. So consider the subset Z. Of the plane consisting of all points within distance delta of L. So consider this subset. We partition Z into boxes as in here. And now I will describe it. Okay. Nedir bu ses böyle ya? Sınıf soğuk değil ama değil mi şu anda? Kaloriferler yanıyor, tamam. So, this is the line L, okay? This is region Q and this is region R, okay? So now, what I'm saying is that I partition it into boxes. I know that this should be of distance delta, and this part should be of distance delta. This is the region that I'm interested in. I know that, right? So now I partition it into boxes. Okay, this is a linear line like this. Like these boxes, okay? And each one of these is, okay, this is delta, so the big part. So these are like delta over 2, delta over 2, delta over 2, delta over 2, okay? Each one of them. So these are the boxes. They are squares. Each box is a square of units and delta over 2 each, okay? From what I have drawn, you can see that there are actually 16 squares, right? 1, 2, 3, 4, yes. Okay, this is the end, so this is like, okay. Okay, 16 squares. Yeah, like this. I will prove that there is at most 1 point in each box. That's what I mean by there are not many points. At most 1 point in each box. How will I prove that? Think about a box, one of them. Let's pick this one, okay? It doesn't matter. They are of the same size. Of each Q over 2 each. Okay? So there might be points in this box. Assume that there are 2 points in this box, at least 2 points. So what is the maximum possible distance between these two? They are squares of size Q over 2. So if there are 2 points that are of maximum distance and in this box, What's the largest distance? Square of Q delta over 2, the diagonal. Yes, it's in the diagonal, right? One of them is here and the other is here. And this is the maximum possible distance, right? If there are at least 2 points. Because these boxes are of size Q over 2, what's the distance in this diagonal at most? Q times square root of 2 over 2, right? Q times square root of 2 over 2, right? This distance. So if there are 2 such points in this box, the distance between them is at most Q times square root of 2 over 2, right? Because the worst case is if they are like at the both ends of the diagonal. But this is less than Q, right? But Q was what? This square is in region R. Both points are in region R, right? Both of these points are in region R. But how did I define Q? I defined Q by, I took the ones that are on the left, the points on the left, I took their minimum, the points that are on the right, I took their minimum, and I took the minimum of these 2 minimums. But now my argument leads me to a point where there exist 2 points among which and between which the distance is less than Q. But this contradicts with the definition of Q. It's impossible. Q was the minimum. I mean, both of these points are in region R, in the same region. So we already took care of these points in recursive calls, right? So there cannot be 2 points in a single box. And of course, there cannot be more than 2 points also. So in a single box, either there exists no points or there is just 1 point. Okay? That's what my argument leads me to. This will eventually, okay, there are like at most 1 point in each box. So there are like 16 in this region. And so this leads me to the position, to the place where they are at most 15 positions of each other in the sorted list SY. Okay? If there are 2 points that are less than Q. I just need to look in this region of, there are 16 boxes, and in each box there is at most 1 point. So there are like actually 16 points that I need to take care of. It's a constant region. Okay? So let me write this down again. Consider the subset Z of the plane consisting of bunu zaten yazdık. Sorry. We first prove that each box contains at most 1 point of S. Okay. Suppose that 2 points of S hala bunun düzelmesini bekliyorum. Hmm. 2 points of S lie in the same box. Since all points in this box lie on the same side of the line L these 2 points either both belong to Q or both belong to R. However, any 2 points in the same box are within distance delta square root of 2 over 2, and that is less than delta. This is like delta square root of 2 over 2, which contradicts our definition of delta as the okay, which contradicts our definition of delta as the minimum distance between any pair of points in Q or in R. Okay? So thus, each box contains at most 1 point of S. I mean, I can't wait for this. Sorry. You can write it down or we can continue tomorrow. So it means that each box contains at most 1 point. Okay. Thus, each box contains at most 1 point of S. Okay. See you tomorrow, guys.
See you.